Okay, welcome to the next lecture. So, in the previous lecture, what we have seen is we have seen these formulas which are essentially for a given decay. We were looking at the process which are essentially decays and collisions or cross sections for scattering process. Um, this could be colliders or fixed target, whatever it is. The formula, the most general formula which we have written, contains some kinematic factors which are given by these integrals, which are m square, and then there is something called the matrix element. Say, for example, this is for the decay width. Similarly, for the cross section, there is a kinematic factor given by this lambda function, which contains s, which is an invariant under the which is an invariant collision invariant times the mass squares, and then there is this in, which is a kinematic factor. For a given decay or any process, say for example, any amplitude, so what we look at is whether the process satisfies some symmetries or not. Say for example, uh, if this process satisfies baryon number or lepton number, say for example, neutron decay satisfies uh, neutron decay satisfies lepton number, say for example, that sets you some sort of limitation whether such a process is allowed or not. Similarly, you can have, so you'll ask for symmetries. So you'll ask symmetries which are like baryon number, lepton, neutron going to proton, electron, antineutrino. Now, if you ask the question, neutron going into proton, electron, and a neutrino, that will not be allowed by symmetry reasons. Okay, and the other one would be if it is allowed by kinematic reasons. Say, for example, if proton, a neutron is slightly heavier than proton. Now, if you revert the process and ask proton going to a neutron and electron and an antineutrino, that will not be kinematically possible as long as electron and a neutrino have a small mass. Strictly speaking, say for example, their masses are very very small compared to the proton mass. But I'm saying that that will not be possible kinematically. Okay. Similarly, uh, I remember telling you that I'll tell you a story about pion and muon. Uh, so for a long time, people couldn't distinguish pion and muon actually. Uh, they looked very similar, so they was not sure which was a pion and which was a muon. Okay, now we say that this the longer track is a muon and the smaller track is pion and everything. So which was heavier was not known, whether it was a muon or which is the pion, which was not known. So people were looking at other decay modes, okay, of the muon, say for example mu to e gamma or something like that, so that they can distinguish muon with the pion actually. So, so that's the fun story. Now we know that it's very trivial that the pion always decays, most of the time decays into a muon and then muon neutrino, antineutrino, muon neutrino, or an antineutrino, depending upon the sign of the pion. So these, but in addition to the symmetry factors and the kinematic factors, an important part is played by this factor, which is essentially m square. So there are these general symmetries, and then there are these kinematic factors which tell you such a decay or such a cross section is allowed or not. These kinematic factors are roughly nothing but for energy momentum conservation. So whether such a process is allowed by energy momentum conservation or not in the relativistic sense. Then the other question is whether it's allowed by the dynamics or not, actually, whether such a process is allowed by the interactions of this particular uh, system. Say, for example, can you have uh, electron interacting with strong interactions? Okay, electron and muon having strong interactions. Say, for example, that would require electron and muon interacting with each other with gluons. Okay, you know that is not allowed now, but suppose if you are just given the particle table and said write down all possible interactions between everything, you can ask the question why the muon doesn't interact with a gluon, say for example. That's a valid question. So, but that question is invalid. You can make it invalid by saying, I know all the interactions of the muon, and I know the gluon doesn't talk to a muon because the muon doesn't have color charge. Okay, so the importance of this m square is also not underestimated. It also tells you how much the strength. So taking into consideration all the kinematic factors and everything, what is the strength of a particular interaction for a particular decay width or a particular decay rate or something. Things which are hyper allowed, say for example, let's take a very very rare process, for a process which is allowed very much by the phase space. There is a lot of space which is allowed for a certain process. Say for example, let's take a process like B to S gamma. So there is some process between two decays. There could be a lot of region allowed by the decay width. Say for example, this integral tells you that, oh, there is a lot of parameter space for this decay width to happen. But this capital M square can tell you, no, that should be, even though the decay width, there is a lot of phase space available, the decay width is highly suppressed or highly allowed by this particular M square, depending upon what kind of an interaction it has. The interaction could be highly suppressed, the rate of the interaction could be highly suppressed, or the rate of interaction could be very large. So this M square also plays it's a combination of both these things which plays an important role to study any of this process. Okay, so the decay weights or the cross sections. So both these things are playing together in understanding most of the process and our understanding of nature. Okay, so to understand our nature, so we need to know how to compute this m square. So the matrix element m square is typically given in this particular format, which is called an S matrix. So this is this is the set of all incoming particles. Say for example, in the E plus E minus collision, the in states are E plus and E minus. For the general process A, B going to n particular final states, so which we had done in the last previous class, A and B are the incoming states, so incoming particles. And the final states could be anything, like for example X particles, which we have seen in the earlier case, or they could be say n particles, which we have seen. They can go into n number of final states particles essentially. And this is a matrix which takes all the states, incoming states, into the final states. This is where all the interaction and the information about the interactions is coded in. This is called the S matrix. So you compute this S matrix element through something called the Feynman diagrams. So one of the key computations, or the important point in these S matrix elements, is the in states and the final states are essentially treated as free particles. This is a very important point, that these are treated as free particles completely. Okay, so the in and out states are considered to be free particles, and the interactions happen only at certain things which are called vertices of the Feynman diagrams. We'll come to that. So all the interaction information is contained in this particular S matrix, which is confined to certain things called the vertices. Okay, all the interaction information, and the in and out states are taken to be as free particles. But remember, these are not free particles in the quantum mechanical sense. These are free particles in the relativistic case. Okay, so our first step towards computation of this matrix element would be to understand what these free particle wave functions are in the relativistic quantum mechanical sense. So what are these relativistic wave equations? So this is what we had to first derive and understand them. This is the first step what we are going to do. Okay, so in this class I'll try to introduce you to one of the first relativistic wave equations which we will deal actually. So in the previous class I have been telling you about that Lorentz transformations uh, are written in terms of some sort of a group. The group is called the Lorentz group, and the Lorentz group is given by SO31. Together with space translations, which is written in terms of this A mu here, the entire Lorentz group becomes something called a Poincare group, which is a bigger group than Lorentz group. Okay, and the study of representations means how various kinds of particles transform under this Poincare group is one of the first thing. So if you know all the representations, you know all the particular particles. So what does Poincare group representations tell you? It classifies all particles in nature in terms of their masses and spin. I didn't write masses here, but so especially in terms of their masses squares, in fact. So in their terms of their masses and their spin. So there are only two parameters which you can classify all the particles with. So you can so let's take the masses to be real and everything. And so what are the spins of these particles? And the relation between the Poincare or the Lorentz group. So it tells you that spin zero particles transform as scalars. So scalars means there is no index. I introduced these concepts of scalars, vectors, okay, in I think the previous lecture 3 or something. So I think you can look into it. So scalar means spinless particles. All the spinless particles transform as scalars under the Lorentz group. So like phi. So this is a scalar. So we looked at various other scalars also. ds square, dot product of two momenta p dot k. Okay, m square, the mass squares, essentially p mu is also a scalar. So all these scalars which are invariant under all Lorentz group transformations, the spin zero transforms exactly like a scalar. So that means it is represented by a function phi of x and t. I didn't write x and t here, which has no Lorentz index. The index, there is no Lorentz index. So it doesn't have any index. Okay. All the spin zero particles transform. What about spin one particles? The spin one particles transform as vectors. Say, I was telling you that the A mu is a vector potential also. So vectors are essentially del mu or the derivative term, or p mu is a vector, and so on. So there are various vectors which we had written down the other day. Actually, A mu we have written, p mu, k, all the momenta. X mu is also a vector. All the position for all the four vectors. So all the four vectors. So a spin one particles also transforms as a four vector under Lorentz group. Exact. Okay. This is a vector, so it carries a one index. So for this reason, a mu, which is the vector potential, represents this is so. Suppose spin one particles. The examples we have seen are a photon. Then there is this gluon, W and Z. All of them transform as a one index vectors. It's like, for example, photon is given in particularly given in terms of some A mu. Okay, and then W mu, G mu for a gluon, W mu for a W particle, and so on. Then spin half, I didn't mention it. Okay. Then what about spin 2? Okay, this is not spinor. Sorry, this is a mistake. I'll note it down and correct it actually. This is not spinor. I'll come to spinors. in the next lectures. Okay, spin half I'll come into. Let's go to the integral spins essentially, and then we'll come to half integral spins later on in the next lecture. So, so half integral spins are essentially called spinors and so on so and higher terms. So spin 2 has two indices. So if we have a graviton, say, so if you want to build a theory of graviton, so you need to have spin 2 particles, and the spin 2 particles are represented by functions of x and t, okay, which have two indices. These are all functions of x and t. Okay, so uh, so one nice thing is, depending upon the spin, what is the kind of representation? Meaning this is the representation. So spin 0 transforms as a scalar. That means it's invariant under all Lorentz transformations. Spin 1 transforms exactly how an x mu or a p mu transforms under Lorentz transformations. So you have spin 1 vector is represented by a mu. Spin 2 transforms like what happens with an h mu, how it transforms. So it has two Lorentz transformations. It transforms like a vector. It transforms like a tensor. So this should not be spinor. This should be a tensor. Let me note it down. Spinor should be replaced by tensor. Okay, that's a typo. So what about spin half particles? So half integers particles, these are called spinors. I'll introduce them in the Dirac equation, which hopefully I'll start in the next lecture after this lecture. Okay, so all the half integer particles have different representations other than the ones. So all the integer particles are just very easy because they can just keep increasing the indices depending upon the spin of the particles. So in the next lecture, I'll hope to introduce Dirac equation, uh, where we'll study about spinors actually. Okay, yeah. Let's see. Okay. So now the next part is, let's focus on the lowest thing, which is the spin zero. Okay, today we'll look into spin zero by relativistic wave equation. So we'll do this relativistic wave, derive this relativistic wave equation in the same way we revised quantum mechanics in the first lecture, or first or second lecture. I don't, maybe, yeah. So in that, we started with again the same Hamiltonian equation, or the energy momentum relation. Okay, for the non-relativistic case, E is equal to p squared by 2m. So we'll do the same thing, but we start with the relativistic energy momentum relation, which is given by p mu is equal to m square, and expanding the p mu, we have E square is equal to p square plus m square. P square here is the 3 momentum. Now identifying E with the Hamiltonian, and we can expand it in terms of the operator, the differential operator E is equal to I del by del t. Okay, and P bar is identified by minus I and I bar. So this is a scalar equation. This is not just an. This is just a ordinary equation. Now we want to expand it in terms of this, express it in terms of the operators. So we express all these variables, observables in terms of operators. So these the differential operator corresponding the Hamiltonian would be I del by del t, and for the momenta would be I minus I del. Now putting them back, this gives you this particular relation. So minus I del by del t square phi minus del square plus m square phi. Surprisingly, this equation was the first equation which was actually derived by Schrodinger before the non-relativistic equation. Okay, but he didn't publish it. He was afraid of publishing it because it had double derivative in time. Okay, he was not sure what to do, and it also gave the problems which we'll see now actually. So that was the reason why he didn't publish it. But immediately later on, Klein and Gordon have published it. It is said that Louis de Broglie also had this equation around the same time, 1924, 25 actually. So this equation uh, is called the Klein Gordon equation. Um, Nowadays, but it has several people had derived it, like I have written here, independently. So the left hand side is the double derivative with respect to time, and the right hand side is single double derivative with respect to space, and then the sum square operator acting on the sum wave function phi, which is a scalar, so spin zero particle. Now in four component notation, you can simply put it back all of them here in one particular side, and this gives you this particular relation. Del mu phi minus, sometimes this del mu is also written in terms of box. So phi minus m square phi is equal to 0, and del mu is equal to this one, depending upon the meter. Good. That's simple. So we have the first relativistic equation, and now what we have to look at is what are the possible solutions. It's a double derivative, and so we look for some simple solutions for it. The simplest solution for this equation is phi, and it's just a plane wave, but it's a relativistic plane wave. So phi is some normalize up to a normalization factor exponential of I p bar x minus et. Now you can take this solution just to verify it. You put it back into the equation of motion, which is the Klein Gordon equation, and you see that this equation satisfies the energy momentum relation E square is equal to p square plus m square. You put it back, take the derivative with respect to time, take the derivative with respect to p, and then equate on both sides, and you end up having this particular relation E square is equal to p square plus m square. But the problem is there is also one more solution, which is phi is equal to n minus e per px plus et. Okay, this also gives the same energy momentum relation E square is equal to p square plus m square. You put it back into this uh, Klein Gordon equation, derive it, and this wave also has E square is equal to p square plus m square. So this is where we have started with, but you end up having with two solutions for the same equation. One with positive energy, another with negative energy. Okay. So if I write this plane wave as px, if px is equal to px mu x mu, so you have both e per px and e per minus ipx give satisfactory solutions for the Klein Gordon equations with energies E is equal to plus minus square root of p square plus m square. Now, it turns out, much later we will say that this seems like a problem because you don't know what negative energy means. So that means you're looking for a single unique solution for this particular equation, and then you end up having two equations. One looks like unphysical because it has energies which are negative. It turns out that this is true for almost every relativistic equation. Almost every relativistic equation, this is true. Okay. Uh, I think this will be dealt in great detail by Apurva in his Quantum Mechanics 3 course. If somebody are going to listen to it, I mean, auditing it or crediting it, I think this will be a good place to look at because he goes in great detail about various things which I'm telling in this class, which I'll cover in one class, but he'll go through several classes in great detail. Okay, so that I think he has also NPTEL lectures on relativistic quantum mechanics on YouTube somewhere. Um, so I suggest you guys look into it Okay, so this seems to be a problem. So what are you going to do with these negative energies? Are these physical? Are these unphysical? Or uh, can we simply ignore them? And how do we interpret this wave function phi? Does it mean that this is a particle with a positive energy, or this is a particle with negative energy, or this is particle with both the energies? How is it? Or we can just throw away these negative energies. One of the ideas was put up by Dirac in the context of Dirac equation, which I applied it here. So, the idea is that in the nature, all the negative energy states are completely filled up. So suppose if this is the energy axis and the states are lined up like this, okay, along the axis. So you have negative energy states here, and then there's a zero, and then there are all these positive states. For simplicity, I just took momentum to be zero, so they have solutions which are like this, e power I empty. So what Dirac said was that suppose all these energies, negative energy states, are completely filled up in nature. All this. So this is called the negative energy solution, Dirac sea. This entire particles which are filled up here, which have negative energies, they're all completely filled up because uh, typically we say that energy should always be positive, and negative energies are considered unphysical. You cannot measure them in an experiment, and so yeah. So what does it mean that these are? So what he said was that okay, these are all they exist, but these negative states, but they're all filled up. So all we had to do is deal with positive energy states, and in a way you can think of um, neglect them, but that's not the entire thing. But if you take this Dirac sea seriously, it has very interesting solutions actually, which has the moment you put in interactions. So once in a while, uh, what happens is uh, this Dirac sea gets hit by a photon or twice the mass of the electron. So, for example, let's build this entire setup for electrons, but scalar particles. No, so for example, neglecting the electron spin, we'll just say that it's also valid for electrons, but uh, say for example for pions. So all these states, say for example, all the negative energy states are completely filled up. So pions are all these negative energy pion states are completely filled up, and then there is a zero, and then all these are positive energy states. But once in a while, there is a photon which comes with a mass of around twice the mass of the electron or pion or whatever. Some what is a particle here at discussion, and then knocks out one particular this negative energy particle from here, okay, and brings it to a positive energy state. So it gives it, say for example, if it has mass of the twice mass of this thing, mass of the particle, so its energy is say neglecting the momentum, for example, its energy is just the mass of the particle. Okay, if it gets twice the mass of this, so with this state, negative energy state is at rest, is essentially 2 minus m, right? So it hits by 2m, so it jumps to here. It jumps to plus m. Okay, yeah, minus 2m, m minus m plus 2m is equal to plus m. So it jumps here. As a consequence, you will create one particular particle of positive energy state. Okay, and then there is a hole left here. There is a hole left here. So this positive energy state will be acting like a normal pi plus or something, and then there will be some hole which will be left here. Which so let's just take electrons only. Say for example, this is an electron of positive energy, and then there could be a hole left here, which will act like a positive energy state, according to Dirac, like a positive energy antiparticle, or a part and a positive energy state with all the quantum numbers reversed. Okay, it is like a, so this hole will act like a positive energy state. Okay, so what does this photon do? It creates a particle and a hole, and this hole essentially acts like a positive energy state, but with all the quantum numbers reversed, all the quantum numbers. So it is lying here essentially. Okay, with this is the origin of the idea that it is could be an antiparticle. Okay, it could be an antiparticle. Antiparticles don't carry negative energies; they carry positive energies, but all the quantum numbers are reversed. Like, what do you mean by all the quantum numbers? Like, for example, if their charges are reversed. So if it is a positive energy star, it will have negative energy, negative charge. Okay. If it is a positively charged, this will be negatively charged, or if this is negatively charged, this will be positive, so and so. So this concept is slightly um, uh, meaning subtle to understand. So this is the point is that there could be a hole. The hole has there is an absence of a state, because there is an absence of the state in all the negative energy states, that is reflected in the positive energy state as a particle which is having opposite charges. So it will start reflecting it. Okay. So the Dirac, as long as the Dirac is completely full, you don't really care about it. Okay. But the moment there is one hole in the Dirac, you start seeing its implications in nature in terms of antiparticles. Now you know that in the so when Dirac gave his theory for the um, positron, soon enough the positron was discovered because it has same mass of an electron but with opposite charge. So it has the opposite curve in the under the magnetic field. So it was immediately discovered, very soon discovered, and so the antiparticle picture came completely came under validation. We got really good validation actually. But people were okay. This was one of the resolutions, but this was until Dirac came. But before Dirac came, people were not happy with these negative states. Okay, people were not really happy with this. What is this negative energy states? How do we get rid of them? And how do we simply ignore them? And so on. So there is another problem with the Klein Gordon equation. Now we start with the Klein Gordon equation, and we can derive a continuity equation for the probability current and density. Suppose if you have this Klein Gordon equation given by this particular equation, del mu minus m square is equal to 5 is equal to 0. Now you can take the complex conjugate and multiply it on the left for this equation. And then now take the Klein Gordon equation for its complex conjugate. For the complex conjugate, del mu phi minus m square. Okay, there is no phi here. Sorry, there is one more typo here. There's no phi here. Take the complex conjugate and multiply with phi again on the left and subtract 1 from 2. Okay, subtract 1 from 2, and this gives you this relation which is written in terms of del mu j mu is equal to 0, where j mu is phi star del mu phi minus phi del mu phi star, where j mu is called the current 4 vector. Okay, current 4 or the probability current 4 vector, which can be expressed as j mu is equal to minus rho j bar. Rho is a scalar quantity which is the probability density, and j bar is the probability current. Now, if we expand this, so you get rho is equal to phi star del 0 phi minus phi del 0 phi star. Now, if you remember this in Schrodinger equation, if you do the same analysis, rho will not have a derivative because uh, rho ends up just being phi star phi. You don't really have phi star del 0 phi minus phi del 0 phi star. The reason why there is a derivative coming here in del 0 because it's a double derivative in time. Okay, it's a double derivative in time. So, and j bar is given by almost the same expression as in Schrodinger equation. Now, the problem with this particular definition or this derivation of this probability density is that rho need not be positive definite. Why this is not always? It's not like phi star phi, so which is a probability the radius of a complex number. Okay, it is phi star del phi and phi del phi star. So it's a you can choose your boundary condition for phi and del phi because it's a second order differential equation. You can choose your boundary conditions in such a way that rho could be negative. Okay, nobody stops you to choose a boundary condition where rho is not meaning negative. In principle, you can choose a boundary condition for that. So the theory doesn't automatically forbid you not choosing a boundary condition. Okay, doesn't forbid you to make rho negative. Like for example, in the Schrodinger equation, rho is always positive definite. But in the case of Klein Gordon equation, rho need not be positive definite. You have a freedom, you have a choice to. The theory doesn't predict that rho is positive definite. You have freedom and choice. By choice of boundary condition, there is a region in which this could be rho could be negative. This is a worry for some problem because that means not only there are negative energy solutions, then you will also have to deal with what to say about probability density being negative. What does it mean? What does it mean? Now you should, okay, this problem conundrums can be resolved the moment you start putting interactions. But even with interactions, you have to be extremely careful. So all these problems with Klein Gordon solutions tell you that some uh, uh, there is some deeper issue with Klein Gordon equation. Okay, the way we are solving the Klein Gordon issue. So suppose if we cannot just say that okay, I neglect completely the negative energy solutions. Now what happens? So let me put some interactions. In the presence of interactions, let's take presence of electromagnetic interaction. So let me say that I have a potential. So I'm just treating the interactions as non-relativistic. They are not. They should be treated in principle with relativistic case. But let's just for the present, let me just take it as some potential del me minus phi square of V of R, some electromagnetic potential times phi is equal to 0. Now what will I do? I ignore the problems with negative energy states. I ignore the problem with probability density going negative, but I still continue the equation. I just say, let me see what this equation gives you if I put in some electromagnetic potential. So I ignore the negative energy solutions and consider only phi is equal to e power minus I rpx. Okay, positive energy. The calculation will not be consistent. The problem is what happens is due to the presence of the interactions, negative energy states will start reappearing in the calculation. Okay, so phi cannot be considered as a single particle solution. Inherently, it contains a multi-particle solution. So even if you try to neglect the negative or negative energy solutions, those solutions will start reappearing the moment you put it back into the you switch on say interactions or if you start playing around So it need not be, say, for example, there are several cases in relativistic quantum mechanics you study. You not just the electromagnetic potential, you put a step potential or any other potential. It leads to a lot of problems actually. There are several problems which you face. But in the presence of interactions, you can solve the problem with the probability density and probability current. What you will say is that phi represents a positive energy particle, phi star will represent a negative energy star particle. So the probability density is not the probability density in the sense of, say, Schrodinger or so and so, but it's actually the electric charge density. Okay, because there is a electric positively charged particle with phi, and phi star contains a negatively charged particle. Okay, so the probability density is nothing. This rho is actually electric charge density, and the probability current is the electric charge current. So the electric charge, or the flow of the electric charge, or the flux of the electric charge. So this is the you can get rid of this problem with probability density and probability current density. But still, the moment you put in interactions, you have to be more careful because uh, you cannot deal with classical interactions. There are other these are problems. So what you do uh, is that you don't treat it as a single particle state, but you start dealing it as the moment you are putting this interpretation, you are already assuming that phi is a particle with a positive charge and phi star is a particle which will be identified as an antiparticle because it has the same mass and same spin as the particle, but which has an opposite charge. So it is a negative charge, and so you write down some interaction. This is the full. We'll come to this interaction a bit later. Okay, this will be the full Lagrangian with interactions, and from there you can derive the equations of motion and everything. So where del mu has the interactions with a electromagnetic field actually. So this capital derivative mu has an interactions with electromagnetic field. So as of now, don't worry about the details about this Lagrangian, but it tells you that here I'm not treating the interactions as non-relativistic, but as a relativistic case. Okay. The moment if you put in full relativity and further start treating phi uh, a particle as a multi-particles system. That means it has two solutions. So one with a particle with a positive charge and phi star is a particle antiparticle with negative charge. Then most of these problems starts dissolving. They start resolving. Most importantly, the problem with a probability current and probability current, probability density and probability current density. Secondly, now phi will be associated with the positive energy states will be associated with particles, and the negative energy states will be associated with antiparticles. So that way you resolve the entire issue, saying that phi is now a complex, no longer it doesn't solve, meaning interpret as a single particle state, but it shows a particle with it's a particle and antiparticle together. It's not a one particle system. It is a particle and antiparticle state, and that's the reason now we start calling it as a quantum field. You don't call it as a wave function, but you start calling it as a field actually. So one of the first ways is essentially to reinterpret the entire thing, okay, as a quantum field where it has where it gives rise to several particles and antiparticles together. Phi will represent an operator now with a positive charge, creates particles with positive charge, and phi star with antiparticles. So the rho would give me in terms of the electric charge. So there will be an electric charge will appear here, and so phi star del mu 0 phi 0 phi del mu phi star. So electric charge will appear here. So rho is no longer the probability current density but electric charge density. So it could be negative in a place where there could be more antiparticles. It could be negative. And the continuity equation just tells you the conservation of the electric charge. So the entire point, this thing is that the relativistic quantum mechanics is not a consistent theory. Okay, but these wave functions are useful. So we interpret phi in terms of a quantum field. Quantum field tells you that, okay, we'll come to it. Okay, in terms of quantum field, and the negative energy states are now associated with antiparticles. So the negative energy states are associated with antiparticles. Now, phi is a quantum field, means phi is reinterpreted in terms of an operator. The field means it's nothing but, so in the Klein Gordon equation, all the things will be written in terms of operator. An operator now is consistent of n number of harmonic oscillators. So phi is not a single particle wave function, okay? But these wave functions will be useful as we will see later actually. So phi is now a multi-particle wave function operator, and you have to define a Lagrangian through which you can derive the equations of motion for this. So you write a Lagrangian density, and phi is interpreted as creator of particle states. This is a creator or annihilator of particle states, exactly like what you do in say harmonic oscillators. So for example, you have the creation and annihilation operators in harmonic oscillators in quantum mechanics. That's similarly what you do here also. So phi is written in terms of harmonic oscillators for all possible momentum. So there will be, for each momentum state, there will be one particular harmonic oscillator. But still, that's still a problem. So that's still a problem that what do you mean having an particles having negative energy? Okay, what do you mean by particles having negative energy? So, but antiparticles are still physical and they carry positive energy by some interpretation given by Feynman and Steckelberg. What I can say is essentially that if you take a wave function of an antiparticle, so phi to be some e power ipx minus ipx, so this contains something like a e minus et plus px, so it is e power it, e power iet. E power iet can be written as minus e minus t. So this is a negative energy solution, but traveling backward in time. Say positive, sorry, you can reinterpret as a positive energy solution, but traveling backwards in time. So t, so it is coming from the past of the wave function of the light cone. So it is coming from the past of the, it's traveling backwards in time actually. So it is something which is coming from the opposite direction in the light cone. So it's traveling backwards, and that's the interpretation given by Feynman and Stein. So that's how you can understand that antiparticles are physical and they carry positive energy, so that you can actually see them in the experiments. That's what we have seen, but they are the ones which are traveling backwards in time. That way you can reinterpret it. So as I said, phi is now expressed in terms of a quantum field, which is an operator. So it is phi star, it will be a creator of antiparticle states, and phi is expressed in terms of harmonic oscillators, series of harmonic oscillators. So essentially, phi of xt is written in terms of this integral dqp by 2, where ap is an annihilation operator of a momentum state p given multiplied with its particular with a particular wave function, and a dagger p is given by its it is a creator with a positive energy wave function actually. Okay, I think okay. If it is a complex field, there should be two kinds of a and a bar. This should be, there is another mistake I have written. This should be a BP actually. This should be another thing. Okay. If it is a complex scalar field, if it's a real scalar field, what I written is correct. Okay, it's a complex scalar field. That means there are two different kinds of operators, A and B. Okay, one for phi and one for phi star. A, B. Okay, there is a typo. here, which I'll correct actually. So this bunch of these are essentially apart from the typo, you can see that this A and A dagger are exactly like in harmonic oscillators. So this is a creation operator and this is a destruction operator. So what we would be interested in, we will not go into the complete details of the quantum field theory. What we need is that this wave function phi, when acting on vacuum, creates a particle with a negative energy, okay, or with a positive energy for an particle, and or it annihilates a particle state, okay, and if it is an A dagger operator acting on a vacuum, it creates a particle with a negative energy, positive energy state. And if you want to create an antiparticle, there is another operator, say for example B dagger, which creates a particle with a negative energy state, which is an antiparticle. So both these operators are particles will be created by applying these particular operators or the corresponding of phi or phi star on vacuum. And they give you these wave functions, which are just the plane waves, one corresponding positive energy and one corresponding negative energy. The negative energy wave functions correspond to a single particle state, which is an antiparticle, okay, and a positive energy state correspond to a particle, which is single particle actually, wave functions. So phi dagger will give me an antiparticle with a momentum p, okay, with this particular e power I px, and phi p will create a particle with a momentum p. So this is what this creates. So these are the wave functions which will be interested, and these are the wave functions which will act as the in states for the interactions which we are going to have here. So for the entire process, what we have considered so far, this will be the in states for whether it's a particle or an antiparticle, as long as the spin is 0. When the so if it is not a charged particle, what happens? This relation, this quantum field I have written here is for a chargeless particle. For a charged particle, there will be two different kinds of creation and annihilation operators. One for phi and one for phi star. Okay, or in terms of the linear combinations. Okay, so I'll correct this typo and load the new slides actually. Okay, so what we'll deal with the in states for spin 0 particles would be something like this: a plane waves. Okay, they don't have any other things, but and with a given momentum. These will be your in states for the S matrix calculation. So these will be represented by dashed lines like this. So the incoming plane waves will be, for a particle, will be like this represented, and an antiparticle would be like this. These are the free particle and antiparticle wave functions. Okay, for a spin 0 particle. So what we have done today is studied the Klein Gordon equation and revised some problems with it. Essentially, the problem with negative energy states and negative probability density, and then we resolved it by okay, we didn't go into the complete details, but we resolved it by introducing something, reinterpreting the wave function as a multi-particle wave function, writing it in terms of some combination of harmonic oscillators for every momentum, and then got the free particle wave functions for particle and antiparticle for the Klein Gordon field. Okay, this is sufficient for us. More details can be found in say quantum field theory course QFT1. Okay, we'll start with this, and now we'll look at free particle solutions of spin half particles in the next lecture. Okay, thank you very much.